Good evening and welcome into the Science Files. I'm Madeline Rowe, and tonight we're opening one of the strangest recovered questions in the archive. Are we living in a simulation? We'll follow the idea from old philosophical doubts about reality into modern physics through probability arguments, quantum mechanics, information theory, cosmic rays, and the limits of computation. We'll ask what kind of evidence could matter, what kinds of claims remain outside the reach of instruments, and why the most careful answer is neither easy belief nor easy dismissal. And if you enjoy these calm, evidence-backed case files, please subscribe, and there'll be another one waiting for you soon. The folder on my desk is thin for a question this large. That is the first warning sign. Some case files arrive in the archive swollen with instrument logs, telescope images, samples, measurements, and failed models. They have mass. They have the stubborn texture of a thing that has been handled by many careful hands. This file is different. Its cover is pale grey, burned along one edge, and the label is written in a typeface that belonged to the last human academic repositories. Simulation hypothesis. Testability status. Uncertain. The uncertainty is not a flaw in the file. It is the subject. Back in my office, which sits beneath the forward observation dome of the research vessel, the hull curves into dark glass, and the stars appear fixed until the guidance system refreshes the view. On the desk, the archived documents rest beside a small lamp, 2 diagnostic tablets, and a strip of old adhesive marked with a simple warning: distinguish question from model. That sentence matters here. The question is enormous. A model is smaller. Science works on the smaller thing. The claim that reality is simulated can be made in a way that no experiment could ever reach. Somewhere beyond our universe, in some inaccessible parent reality, there could be a system with unknown laws, unknown purposes, and unknown capacities producing everything we experience. A claim like that may be emotionally powerful. It may even be logically possible. But if it cannot make predictions that differ from ordinary physics, then it has no handle for science to grip. The testable version must be narrower. It must say that if the universe is simulated in a certain way, then some feature of that simulation may leave a mark. Perhaps spacetime has a hidden lattice. Perhaps a finite resolution model distorts the motion of the highest energy particles. Perhaps computation has a cost so large that certain simulations are physically impossible under known laws. Perhaps the hypothesis makes probabilistic claims, and those claims must be handled with care. The file begins there, at the boundary between a frightening idea and a measurable one. There are questions that humans seem to have carried long before they had machines powerful enough to inspire this particular version of the question. They wondered whether the world was as it appeared. They imagined dreams inside dreams, shadows mistaken for bodies, deceivers with power over the senses, minds trapped inside the limits of their own perception. The old records preserve names from several civilizations: Plato, Zhuangzi, Descartes, Berkeley. They did not speak of graphics processors or quantum computers or ancestor simulations, but they knew the shape of the unease. How can a mind be certain that the world it experiences is the world as it is? For most of history, that question belonged to philosophy and theology. Then the machines arrived. By the late 20th and early 21st centuries, humans had built digital worlds that were crude, finite, and unmistakably artificial, yet increasingly convincing in narrow ways. They simulated weather, galaxies, nuclear interactions, traffic, protein folding, aircraft turbulence, and the spread of disease. They rendered fictional spaces where light, motion, and collision were not physical events, but calculations. They began to use computation not only to store knowledge, but to imitate processes. That was the change. Once a civilization understands simulation from the inside, it can begin to ask whether it might also be inside one. The modern form of the simulation argument is usually traced to the philosopher Nick Bostrom, writing in 2003. His argument was not an instrument reading. It did not claim that a telescope had detected pixels in the sky, or that quantum mechanics had exposed a computer behind the universe. It was a probability argument, built from a set of conditional claims. Bostrom asked us to consider advanced civilizations far beyond present human technology, capable of running detailed simulations of their ancestors. If such civilizations exist, if they choose to run many such simulations, and if simulated minds can be conscious, then the number of simulated people with experiences like ours could vastly exceed the number of original biological people. Under those assumptions, a person asking the question might have reason to think they are more likely to be one of the simulated minds. The argument is often compressed badly. In the archive, I find many fragments where it was repeated as if it said, "We are probably simulated." That is not careful enough. Bostrom's actual structure is a trilemma. At least one of three propositions is true. Human-like civilizations usually go extinct before reaching a post-human stage, or post-human civilizations are extremely unlikely to run many ancestor simulations, or almost all minds with experiences like ours are simulated. This distinction is important. The argument does not prove the third proposition. It says that if the first two are rejected, the third becomes difficult to avoid. But those first two propositions are not trivial. Civilizations may not survive long enough. They may survive, but choose not to build ancestor simulations. They may lack the physical ability. They may have ethical prohibitions. They may discover that consciousness cannot be generated by the right computation alone. Or they may run simulations that are nothing like ours. Behind the argument sits an assumption called substrate independence. It says that minds do not require carbon-based biological brains in particular. If the right information processing structure is reproduced in sufficient detail, then conscious experience could arise in another physical substrate, such as silicon or some more advanced computing medium. Bostrom did not pretend this was settled. He treated it as a necessary assumption for the argument to start. That is the first hinge in the case file. A mind must be something that can be simulated, not just behavior, not a puppet responding like a person, a mind. The second hinge is capacity. Could any civilization actually run a simulation detailed enough to contain conscious observers with a stable world around them? Bostrom argued that post-human resources might be enormous. Planetary-scale computers, astronomical energy supplies, techniques unknown to early humans. He did not need to prove that such machines were near. His argument could survive long timescales. If physics permitted the machines, and if civilizations persisted, then the number of simulated observers might become huge. The third hinge is motivation. A civilization may be able to build something and still decline to build it. There are many reasons a mature civilization might avoid ancestor simulations. The simulated beings might suffer. The act might be considered unethical. The ancestors might be uninteresting. The computational cost might be better spent elsewhere, or the civilization might have changed beyond the desires of its biological past. When a popular idea depends on hinges, the careful work is to examine them one by one. I leave the office and carry the folder into the archive vault. The door opens with a pressure-softened click, and the air inside is cooler. The vault holds fragments of human knowledge in stacked banks. Papers, images, mathematical notebooks, mission telemetry, classroom lectures, private letters, telescope logs. Most files are incomplete. Some have missing pages. Some are only a title and a corrupted abstract. The simulation file has more philosophy than data, at least at first. The archive table projects a branching diagram above the surface. One line is marked base reality. From it, a set of daughter realities emerges. From those, more branches. Some end quickly, some split. Some become dense enough that the root is almost invisible. This is where probability enters the case. In 2020, the astronomer David Kipping revisited the simulation argument with Bayesian reasoning. He treated the question less as a simple count of simulated versus unsimulated worlds, and more as a problem with model uncertainty. That phrase sounds dry, but it is a guardrail. It means that we should not only count possible simulations. We must also ask whether the model that permits such simulations is true in the first place. If we assume that many high-fidelity simulations exist, then yes, the simulated observers may outnumber the base observers. But that assumption carries weight. It includes technical possibility, civilizational survival, motivation, and the nature of consciousness. Kipping separated the broad possibilities into two models, one in which civilizations do produce Bostrom-like simulations, and one in which they do not. When he applied Bayesian model averaging, he found that, under generous assumptions, the probability that we are simulated remains below 1/2, tending toward 1/2 as the number of simulations becomes very large. That result should not be recited as if the universe has a coin hidden inside it. The important point is not the exact number. The important point is that probability claims are fragile when the assumptions are unproven. Saying there could be many simulations does not give permission to ignore the chance that such simulations are impossible, rare, unwanted, unstable, or unlike our world. The branching diagram above the archive table dims, then collapses to a single unresolved node. That is closer to honest. Humans loved large numbers. The archive proves that repeatedly. 1 billion simulations, 1 trillion simulated minds, infinite nested realities. But mathematics does not make a premise true by multiplying it. A false engine does not run faster when scaled up. Science asks for a different kind of handle. It asks what would change in the evidence if the hypothesis were true. There is a problem here that appears again and again in the file. The simulation hypothesis can retreat faster than any test can advance. If a test finds no hidden grid, the simulation may not use a grid. If physics seems continuous, the simulator may be using a better method. If computation seems impossible under our laws, the parent reality may have different laws. If all observations match ordinary physics, the simulator may have designed them to do exactly that. A hypothesis that can absorb every possible observation is protected from failure, but that protection comes at a cost. It stops behaving like a scientific model. This is why the question must be narrowed. We cannot test any possible simulation by any possible simulator. We can test a model with structure, a finite resolution lattice, a limited computational budget, a rule for when information is generated, a prediction that differs from the standard theories. That is where the case file becomes physical. In the instrument room, the ship's processors sit behind glass panels, warm racks threaded with light. I can hear the cooling system breathe through the floor. A vessel like this makes computation feel less abstract. Every calculation leaves heat somewhere. Every stored bit occupies a physical state. Every model has a cost, even when the cost is hidden behind polished interfaces and steady indicator lights. This is one of the central lessons of 20th century information physics. Information is physical. Rolf Landauer made that sentence famous. It means that information is not a ghostly substance floating above matter. It is recorded in physical systems, a magnetic domain, an electric charge, a spin, a photon polarization, a molecular arrangement. To process information, a system must change physical states. To move information, it must send physical signals. To erase information irreversibly, it must pay a thermodynamic price, at least k times t times the natural logarithm of 2 for each bit erased, where k is Boltzmann's constant and t is temperature. That number is tiny for a single bit. It becomes less tiny when the number of bits becomes astronomical. There is a subtlety here. Reversible computation can, in principle, avoid some of the energy cost associated with erasure. A perfectly reversible calculation does not have to throw away information at every step, but real computation requires control, memory, correction, communication, and eventually some contact with the physical world. Error correction, in particular, is not optional for fragile systems. In a universe with noise, heat, and finite precision, keeping information reliable costs something. Seth Lloyd took these ideas and asked how much computation the observable universe itself could have performed. He treated the universe as a physical system with energy, entropy, size, and age. The laws of physics then set limits on the number of bits it can register and the number of elementary operations it can perform. The famous estimate is that the observable universe could have performed no more than about 10 to the 120 operations on about 10 to the 90 bits, at least when considering matter degrees of freedom in a standard cosmological model. If gravitational degrees of freedom are included, related estimates of information capacity can be larger, but the lesson remains the same. Finite physics gives finite capacity. That number is almost impossible for a human mind to hold. A 1 followed by 120 zeros. The archive renders it as a bar of light too long for the table and then compresses it until it becomes unreadable. Even enormous numbers can be bounded. Lloyd's calculation uses several limits. The speed of computation is limited by energy. The Margolis-Levitin theorem says that the rate at which a quantum system can evolve through distinct states depends on its energy above the ground state. More energy allows faster change, but not infinite change. Memory is limited by entropy. Communication is limited by the speed of light. A physical computer is not free to update the whole of itself instantaneously. Jacob Bekenstein's work on entropy and information bounds adds another constraint. For a complete physical system with finite energy contained in a finite region, there is an upper limit on the entropy, and therefore on the information capacity. Black hole thermodynamics and the holographic principle pushed this idea further. They suggested that the information capacity of a region may scale with area rather than volume under extreme gravitational conditions. The details are technical and the boundaries of the arguments matter, but the broad implication is severe. A finite region with finite energy cannot contain unlimited information. This does not answer the simulation question by itself. It does something more useful. It removes magic from the word computer. If our universe were being simulated by a system governed by physics like ours, that system would have limits. It would require energy. It would require memory. It would require time. It would require error correction. It would face thermodynamic constraints. It might have extraordinary resources, perhaps far beyond anything humans built, but extraordinary is not infinite. Back in the instrument room, one of the old diagnostic screens shows a simple operation, a memory cell changing state, 0 to 1, 1 to 0, a microscopic event barely worth noticing. Then the archive scales it upward, a brain, a city, a planet, a galaxy, the visible universe. The tiny operation becomes a storm of requirements. This is where casual simulation language often fails. It treats the universe as if it were a scene rendered on a screen, and a screen as if it were reality. A video game does not contain a mountain. It contains data and rules sufficient to produce a mountain-like experience for a player. If nobody is near the mountain, the game may not render its fine details. It can save resources by calculating only what matters to the observer. Some versions of the simulation hypothesis borrow that idea. Maybe the universe is not fully simulated everywhere. Maybe only observations are generated. Maybe unobserved details are left unresolved until needed. That can sound efficient. It can also become scientifically slippery. The reason is consistency. The real world, as humans measured it, was full of systems where small details propagate into large consequences. Weather depends on microscopic fluctuations. Chemistry depends on quantum states. Biological cells depend on molecular interactions. Particle experiments depend on events far below direct human perception. A simulator trying to render only what conscious observers notice would still need to preserve an enormous network of causal consistency. If a scientist can build an instrument, record data, compare it with another instrument, publish it, and later use the result to build a machine, then the simulation must make all those layers agree. The more science a civilization does, the more expensive deception becomes. This does not make a rendered universe impossible in every imaginable case. A sufficiently clever external system might generate only the right experiences. It might simulate the scientists as part of the output. It might not contain independent observers at all, but every move in that direction makes the hypothesis less testable. Physics works by assuming a reality that does not depend on one mind's private experience. If that assumption is abandoned completely, instruments lose their ordinary meaning. The case file does not close there. It turns instead towards the physics humans did know how to test. One of the oldest traps in this subject is to point at quantum mechanics and say, there, proof. The universe behaves strangely when observed. Particles act like waves. Measurement changes outcomes. Reality must be rendered only when looked at. This is too fast. Quantum mechanics is strange, but it is not a license to attach any interpretation we like. In the double-slit experiment, Electrons or photons sent one at a time can produce an interference pattern when no which path information is available. If which path information is obtained, the interference disappears. That is not because a human eye beams reality into existence. It is because quantum systems are described by states whose possible alternatives can interfere, and interactions with measuring devices entangle those alternatives with the environment. Once the relevant information is physically recorded, the coherence needed for interference is lost or dispersed. There are interpretations of quantum mechanics that speak differently about what is real, what collapses, and what measurement means. Copenhagen, many worlds, objective collapse, relational interpretations, cubism, pilot wave theories. The archive has fragments of all of them. They disagree about ontology, but they agree on the experimental predictions in the regimes where quantum mechanics was tested. A simulation hypothesis must do more than gesture toward quantum oddity. It must predict something else. Some researchers propose tests based on the idea that reality might be rendered only when information becomes available to an observer. These proposals often involve variations on wave-particle duality, delayed choice, or quantum eraser experiments. They are intriguing as thought experiments. They force the question of what counts as a record and what counts as observation. But they depend on a very specific model of simulation, one where conscious observation or available information has a role different from the one it has in standard quantum mechanics. The archive marks these proposals with a caution flag. They are not evidence that reality is simulated. They are attempts to formulate possible tests under speculative assumptions. The difference matters. Aboard the ship, I cross the long corridor outside the research bay, where the wall panels are matte black and the guide lights run low along the floor. The corridor is useful here because it is so ordinary. It has length, it has direction. If I walk from the archive to the observatory, the path is stable. Turn around, and the same corridor returns, with the same pressure doors and the same maintenance seams. The ship does not care which way I face. Physics has a deeper version of that indifference. It is called symmetry. Symmetries tell us what can change without changing the underlying laws. If the laws of physics are the same today and tomorrow, energy is conserved. If they are the same here and elsewhere, momentum is conserved. If they are the same under rotations, angular momentum is conserved. If they are the same for observers moving at constant velocity relative to one another, we enter the domain of Lorentz invariance, the symmetry at the heart of special relativity. Lorentz invariance says, in part, that there is no preferred inertial frame. The speed of light in vacuum is the same for all inertial observers. The laws of physics keep their form under Lorentz transformations. This is not a decorative principle. It is built into the standard model of particle physics and into the local structure of general relativity. It has been tested with laboratory experiments, atomic clocks, particle observations, astrophysical photons, cosmic rays, and many other systems. A naive grid threatens that symmetry. If space were laid out like a cubic lattice, with preferred axes and a fixed spacing, then particles moving along the grid directions might not behave exactly like particles moving diagonally through it. At low energies, the difference might be tiny. At extremely high energies, it might become detectable. The grid could break rotational symmetry. It could produce modified energy-momentum relations. It could leave artifacts, the way numerical simulations can leave artifacts when their resolution is finite. That does not mean discreteness is impossible. Some approaches to quantum gravity involve discreteness without simple preferred directions. Causal set theory, loop quantum gravity, and other models handle the issue in different ways. Planck scale discreteness is not the same thing as a computer screen. The Planck length is a scale formed from fundamental constants, not a measured pixel size. Saying the Planck length exists, therefore the universe is pixelated, is one of the archive's more common damaged claims. Still, a crude simulated universe might have a grid. And if it had a grid, one could ask what the grid would do to particles. This is where the file becomes unusually concrete. In 2012, Silas Bean, Zohre Davoudi, and Martin Savage explored observable consequences of a universe simulated on a cubic spacetime lattice. Their approach was deliberately specific. They did not try to test every possible simulation. They took an analogy from lattice quantum chromodynamics, or lattice QCD, where physicists simulate the strong nuclear force by replacing continuous spacetime with a finite grid. Lattice QCD is not a fantasy. It is a real computational tool used to study quarks, gluons, protons, neutrons, and nuclei. The grid is a method. It approximates the continuum, and the approximation improves as the lattice spacing becomes smaller and the algorithms become more refined. Bean and his colleagues asked, if our universe were an early or imperfect numerical simulation, perhaps using a hypercubic lattice, could the lattice spacing leave measurable effects? They considered several possible observables. Precision quantities, such as the magnetic moment of the muon or differences in the fine structure constant, might constrain certain lattice artifacts. But the strongest bound they identified came from ultra-high energy cosmic rays. These are among the most energetic particles known. Some arrive at Earth with energies far beyond anything human accelerators could produce. They cross intergalactic distances, strike the atmosphere, and trigger cascades of secondary particles. Large observatories, such as the Pierre Auger Observatory and the Telescope Array, detect those cascades across broad areas of ground and sky. The key is that the highest energy cosmic rays are sensitive probes of extreme physics. If a lattice imposes a maximum momentum or modifies dispersion relations, it could affect the cosmic ray spectrum. Bean and colleagues used the observed high-energy cutoff to place a lower bound on the inverse lattice spacing, roughly greater than 10 to the 11 giga-electron volts in their model. More evocatively, they suggested that the arrival directions of the highest energy cosmic rays might reveal a pattern, a degree of rotational symmetry breaking associated with the underlying lattice. If the universe were simulated on a cubic grid, the sky might, at the highest energies, remember the cube. The observatory window is the right place to hold that thought. I stand before the forward glass while the ship's particle monitors sweep the dark. Most of the visible stars are local foreground. Beyond them, the archive overlays faint trajectories, long lines entering from beyond the galaxy, each representing a particle that once crossed fields, voids, radiation backgrounds, and magnetic turbulence before encountering a detector built by human hands. Cosmic rays are not clean messengers. Charged particles bend in magnetic fields. Their sources are difficult to identify. Their arrival directions may be scrambled. Their energies are hard to reconstruct perfectly. The highest energy events are rare, and rarity makes statistics slow. This is why the proposed lattice test is difficult. It is also why it is scientifically meaningful. It does not say, The universe feels artificial. It says, under a particular simulation model, there may be a particular symmetry-breaking signature in a particular energy regime. That is the shape of a test. The caveat is just as important. A null result would not disprove simulation in general. It would constrain or disfavor a certain kind of lattice simulation with certain properties. A more advanced simulator might use an improved lattice action, a non-cubic grid, an adaptive mesh, a quantum algorithm, or a method that preserves relevant symmetries more carefully. The more competent the simulation, the fewer artifacts remain. Human simulations already showed this. Numerical physicists learned how to reduce discretization errors. They improved actions. They refined meshes. They preserved symmetries where they could. It would be strange to assume that any civilization capable of simulating a universe would be worse at simulation than early humans were at lattice Q, C, D. Still, the test matters because it is one of the few places where the idea touches an instrument. The archive table shifts from cosmic ray tracks to a rotating grid. At first, the grid is obvious, thick lines crossing like the framework of an unfinished room. Then the spacing shrinks, the lines fade. The grid becomes so fine that the model looks continuous from far away. That is the old numerical dream, to choose a resolution so small that the artifacts vanish beneath the phenomena being studied. But in high-energy physics, small is relative. A lattice that is invisible to atoms might be visible to particles with much shorter wavelengths. A grid hidden from chemistry might still distort the motion of the most energetic cosmic rays. Instruments do not need to see the grid directly. They only need to see what the grid changes. This is a good place to be careful about scale. The Planck energy is about 10 to the 19 giga-electron volts. The highest known cosmic rays are far below that, around 10 to the 11 giga-electron volts. Human accelerators are lower still. If new physics appears only at the Planck scale and is strongly suppressed below it, experiments face a huge gap. Yet high-precision measurements and astrophysical baselines can sometimes turn tiny effects into constraints. A photon crossing billions of light years can accumulate a delay. A forbidden particle reaction may become allowed if dispersion relations change. A threshold may shift. A polarization may rotate. The universe can become a long lever arm. This is why Lorentz invariance tests became so important in quantum gravity phenomenology. Many theories suggested that spacetime might have structure at very small scales. If that structure broke or modified Lorentz symmetry, small relic effects might appear in accessible regimes. Researchers searched for them in atomic systems, neutrino behavior, gamma-ray bursts, cosmic rays, synchrotron radiation from the Crab Nebula, and precision laboratory measurements. The result was not a simple discovery. The result was a tightening net. Lorentz invariance has survived an extraordinary range of tests. That does not prove it is exact at every scale. It does show that if violations exist, they are constrained, model-dependent, and often very small. This matters for the simulation file because any simple hidden grid story must pass through those constraints. A grid that breaks symmetries too strongly would likely have shown itself already. The central archive chamber is built around symmetry. Its projection system can rotate a model without changing the underlying data. A galaxy cluster turns in the air. The equations beside it keep their form. A particle collision is replayed from another frame. The measured laws agree. I watch the chamber perform the same transformation again and again, and the point becomes physical. Symmetry is not a human preference for elegance. It is a fact about what instruments find when they are turned, moved, repeated, and compared. If a simulated universe preserves those symmetries perfectly, then it may be harder to test. If it fails to preserve them, the failure becomes evidence against that model. This is the burden of every scientific version of the simulation hypothesis. It must risk disagreement with the world. The file now turns to a deeper difficulty. Even if we can imagine testing artifacts, could a universe like ours be simulated at all? The question sounds simple until one asks what must be included. A full simulation of the visible universe down to fundamental scales would require an amount of information comparable to the information content of that universe. It would need to represent fields, particles, gravity, quantum states, thermodynamic histories, and all the correlations among them. If the simulator is outside our universe and has different physics, perhaps those requirements change. But if the simulator obeys physical laws similar to ours, the problem becomes severe. Franco-Vatzer approached this question by combining astrophysical constraints with information energy reasoning. The analysis considered several cases, simulating the entire visible universe, simulating Earth, and simulating a lower resolution version of Earth constrained by high-energy neutrino observations. The conclusion was stark. Under physics like ours, the energy or power needed is either incompatible with known physics or astronomically large, even for reduced cases. A universe with the same physical properties as ours cannot casually simulate another universe like ours at full detail. That phrase, under physics like ours, must remain attached to the claim. It is not a proof against every possible simulator. It is a constraint on simulators that share our sort of physics. But constraints are valuable. They keep the discussion from floating away. I take the maintenance ladder down towards the engine-adjacent passage, where the metal is warmer and the hum is less filtered. Here the ship is honest about its dependencies. Power conduits run behind ribbed shielding, coolant lines shiver faintly. A panel near the bulkhead lists thermal load, reactor output, waste heat, storage reserves. No calculation happens in a place like this without a bill arriving somewhere. The same logic applies to simulated worlds. A civilization can save resources with approximations. It can simulate only what matters for its purpose. It can use effective theories at large scales instead of fundamental physics everywhere. Human scientists did that constantly. Climate models did not simulate every molecule. Galaxy simulations did not track every atom. Biological models simplified cells. Even lattice QCD used finite volumes, finite spacings, and approximations. But approximations have domains. Push them outside those domains, and they fail. If a simulated Earth must support geophysics, biology, chemistry, particle physics, astronomy, and conscious observers who perform precision experiments, then its required fidelity grows. Every instrument becomes a demand for deeper consistency. A neutrino detector asks the simulation to handle neutrinos passing through Earth. A gravitational wave observatory asks it to handle spacetime strain from distant black holes. A particle collider asks it to handle high-energy quantum fields. A radio telescope asks it to preserve electromagnetic signals across vast distances. A fossil record asks it to maintain geological time. A memory asks it to preserve a biological past. One can always retreat to a more radical hypothesis, only the experiences are simulated, not the world. But then the scientific question dissolves into something closer to solipsism. If all evidence, all observers, all instruments, and all memories are generated only as experiences for one mind, then physics has little left to test. The hypothesis may be impossible to refute, but only because it has left the territory where evidence can reach. A good case file does not confuse unreachable with profound. The ship's galley is empty when I pass through it. A cup is magnetized to the counter beside a small panel showing water reclamation efficiency. The galley is a modest room, almost domestic, but it belongs in this file because it reminds me that intelligence eats through resources, even when the intelligence is artificial. Heat must be moved, waste must be processed, errors must be corrected, memory must be stored. Every sustained pattern resists entropy by spending something. Human beings once forgot this when speaking about computation. They imagined software as weightless because they did not see the mines, power plants, cooling towers, data centers, supply chains, and discarded machines behind it. The physics was always there. The same mistake can happen at cosmic scale. To say the universe is information is not the same as saying the universe is easy to compute. A library is information, so is a brain, so is the pattern of air in a storm. But to reproduce the pattern, update it, preserve it, and make it consistent under measurement is a different task. Quantum mechanics makes the task harder still. In classical physics, a system can often be described by positions and velocities, fields and values, probabilities if one lacks knowledge. In quantum mechanics, the state of a system contains amplitudes over possible configurations. For many particles, the number of amplitudes can grow exponentially. 40 spin 1/2 particles require over 1 trillion complex amplitudes for a completely general state. 80 require numbers so large that ordinary memory comparisons fail. Add motion, fields, interactions, and entanglement, and brute force classical simulation becomes impossible very quickly. This is one reason quantum simulation became a field. Feynman argued that if nature is quantum, then a computer meant to simulate nature efficiently should itself use quantum mechanics. Later work showed that quantum computers can efficiently simulate broad classes of local quantum systems, at least in principle. Analog quantum simulators can use one controllable quantum system to study another less accessible one. Neutral atoms, trapped ions, superconducting circuits, photons, spins, and other platforms became possible tools. But a quantum simulator is not a wand. Preparing the right initial state can be hard. Implementing the correct evolution can require many operations. Decoherence threatens fragile states. Error correction requires overhead. Measurement extracts limited information. Some problems remain difficult even for quantum devices. The phrase quantum computer does not erase the constraints of physics. It changes the resources available for certain tasks. For the simulation hypothesis, this cuts both ways. It suggests that a universe like ours may be more naturally simulated on a quantum machine than a classical one. It also shows why a serious simulation claim must specify the nature of the simulator. A classical grid updating like a cellular automaton is a very different proposal from a quantum simulation of fields, and both differ from a parent reality with unknown laws. The old human phrase computer simulation carried too much baggage. A computer did not have to mean a laptop, a server rack, or a digital machine with bits in the human sense. It could mean any physical system whose states and dynamics correspond to the states and dynamics of another system. But if the word becomes that broad, it begins to overlap with physics itself. Seth Lloyd addressed this tension directly. Is the universe a computer? It depends on what one means by computer and what one means by is. The universe is not a conventional digital machine running human software, but physical systems do register and transform information. In that sense, the universe computes its own evolution by being itself. That idea is elegant, but it can confuse the case if handled loosely. Saying the universe computes is not the same as saying the universe is computed by something else. The first is a way of describing physical dynamics. The second is the simulation hypothesis. The difference is the external machine, the parent system, the layer beyond. The file keeps returning to layers. In the holographic evidence bay, the lights dim until the room becomes a black volume crossed by thin projections. A sphere appears first, then its surface is tiled into plank-sized patches. The interior glows, then fades, leaving only the boundary. This is a visualization of information bounds, not a literal map. It shows a strange lesson from gravity and thermodynamics. The maximum entropy of a region may be tied to the area of its boundary. Humans found that lesson through black holes. A black hole has entropy proportional to the area of its event horizon. The generalized second law of thermodynamics, Hawking radiation, Bekenstein bounds, and later holographic ideas forced physicists to treat information, gravity, and quantum theory as parts of the same problem. These ideas do not prove simulation. They do show that reality has information limits woven into known physics. This is an important distinction. Information physics can make the universe feel computational. It does not automatically make it artificial. There are speculative proposals that go further. Melvin Vopson argued for a second law of infodynamics, where information entropy in systems containing information states remains constant or decreases over time, in contrast with ordinary thermodynamic entropy. He applied the idea to digital information, genetics, atomic systems, symmetries, and cosmology, and suggested that it may support a simulated universe interpretation. The archive marks this as frontier material. It is interesting. It is not the backbone of the case. The reason is not that speculative work should be ignored. Science needs difficult proposals at its edges. The reason is that an episode built on testability should not rest its weight on claims that are themselves still contested. Information laws, compression-like behavior, and mathematical symmetry can be suggestive. They are not the same as evidence for a simulator. Nature can be mathematical without being a program. It can be information-bearing without being artificial. It can minimize certain quantities without having an engineer. The older human mistake was to mistake resemblance for origin. A tree branches like a river network. That does not mean the tree is a river. A galaxy simulation resembles a galaxy. That does not mean the galaxy is made of code. A physical law can be written as an algorithm. That does not mean the universe is running that algorithm in an external machine. Still, resemblance can motivate tests. That is enough. The coldest part of the ship is the specimen archive. It holds physical samples gathered across missions, dust grains, ice cores from dead comets, mineral wafers, biological residues sealed under glass. This room is useful for another reason. It reminds me that science grew from contact. A claim became stronger when it met something resistant. A rock, a spectrum, a particle track, a clock, a measured decay rate, a sky survey. The simulation hypothesis has often lacked that resistance. It expands into every gap. But the best parts of the file do meet evidence. Cosmic ray spectra, Lorentz invariance tests, information bounds, computational complexity, Bayesian model comparison. These do not solve the whole question, but they make portions of it answerable. A damaged note in the file reads, "Meaningful tests are tests of commitments." That is the sentence I would preserve. A model commits to something. A cubic lattice commits to preferred directions or lattice artifacts. A finite resolution simulation commits to possible high energy cutoffs or modified dispersion. A same physics simulator commits to energy and information constraints. A Bayesian argument commits to assumptions about civilizations, consciousness, and priors. A rendering model commits to differences between physical recording and conscious observation. Once a model commits, instruments can respond. Without commitments, the hypothesis becomes fog. Human science had many tools for clearing fog, but no tool works without contrast. To detect dark matter, astronomers compared visible mass with gravitational motion. To infer exoplanets, they compared stellar brightness or radial velocity with periodic models. To find gravitational waves, they compared interferometer arm lengths with predictions from general relativity. In each case, something could have been otherwise. For a simulation test, the question is, otherwise, how? If the standard physics predicts one distribution of ultra-high energy cosmic ray arrival directions, and a lattice simulation predicts a cubic anisotropy, then data can compare them. If Lorentz invariance predicts no energy-dependent photon speed, and a quantum gravity model predicts one, then gamma-ray burst observations can constrain it. If known computation limits forbid a certain simulation under same physics assumptions, then the hypothesis must either change those assumptions or accept the constraint. There is dignity in narrowing a question. It may feel less dramatic than asking whether all of reality is false, but it is how knowledge survives. The cartography table holds the next part of the file. It projects a map of Earth's sky as it was seen by cosmic ray observatories. The map is uneven, marked by exposure, detector coverage, and statistical uncertainty. Over it, the archive draws a faint cube, then rotates it. The cube does not fit the sky. It is not meant to. It is a hypothesis looking for a residue. The highest energy cosmic rays are rare. A single square kilometre detector may wait a long time for one. Human observatories spread over huge areas because the atmosphere itself became part of the detector. When a cosmic ray struck air molecules high above the ground, it produced a shower, pions, muons, electrons, photons, a spreading cascade moving near light speed. Surface detectors sampled the particles at ground level. Fluorescence telescopes watched faint ultraviolet light from nitrogen excited by the shower. From timing, intensity, and geometry, scientists reconstructed the original particle's energy and direction. This reconstruction was not perfect. The atmosphere changed. Detector calibrations mattered. Hadronic interaction models at extreme energies carried uncertainty. Magnetic fields bent charged particles between source and detector. Yet patterns could still be studied, spectra measured, anisotropies searched for. The GZK cutoff named for Greisen, Zatsepin, and Kuzmin, arises because ultra-high energy protons travelling through the cosmic microwave background can interact with low-energy photons, producing pions and losing energy. This limits how far the most energetic protons can travel. Observations of the high-energy spectrum show a suppression at the highest energies, though the details involve source physics, composition, and propagation. Bean and colleagues used the existence of high-energy cosmic rays and their cutoff structure as a constraint on lattice spacing in their simulation model. The idea is subtle. A lattice imposes constraints on momentum. At energies approaching the inverse lattice spacing, particles begin to feel the underlying discretization. Their energy-momentum relation changes. The cosmic ray spectrum, especially at the highest energies, becomes a probe of any such modification. The absence of obvious lattice artifacts pushes the lattice spacing smaller, or the inverse spacing higher. But the possible anisotropy is more visually striking. A cubic lattice has symmetries of a cube, not full rotational symmetry. If the highest energy particles become sensitive to that lattice, their allowed momenta might show directional preferences. Over enough events, the sky could show the faint geometry of the underlying grid. The archive project simulated arrival directions beside the observed sky. It does not declare a match. It does not have enough evidence to do so. The value lies in the question's form. Could the sky reveal the numerical method? That is a scientific question. It is also a humbling one. Humans built simulations of fields on lattices because they had to. The continuum equations were too hard to solve directly. They accepted grids, finite boxes, step sizes, approximations, and then spent years learning how to control the damage. If our universe were simulated, perhaps its builders faced the same trade-offs. Or perhaps they did not. Perhaps their physics made our hardest problems easy. Perhaps simulation in their world meant something no human mathematics would recognize. That uncertainty cannot be removed from within our file. It can only be named. I return to the corridor, and the ship drops into a slow attitude adjustment. The stars shift across the overhead glass, though the motion is ours, not theirs. This is a small reminder of reference frames. A person inside a moving room can mistake motion for stillness, unless they have something to compare against. Relativity made that intuition precise and then transformed it. There is no absolute rest frame available to ordinary inertial observers. The laws keep their form. A hidden lattice would be a kind of absolute structure. It might define directions and a rest frame beneath observed physics. If those directions never affected anything, they would be unobservable. If they affected particles even slightly, they would be testable. Modern Lorentz invariance tests are therefore not just side material. They are part of the strongest scientific boundary around spacetime grid claims. If the simulation hypothesis is translated into the universe is computed on a rigid grid, then that grid must avoid existing constraints. It must not cause forbidden particle decays. It must not produce vacuum Cherenkov radiation where none is seen. It must not let photons of different energies arrive with delays beyond limits, unless the model accounts for them. It must not rotate polarization in ways contradicted by astrophysical observations. It must not shift reaction thresholds outside what cosmic rays, gamma rays, and laboratory systems allow. The details vary by model. That phrase must remain present. Lorentz violation is not one effect. It is a family of possible deviations, organized in effective field theories and other frameworks. Some break symmetry with preferred frames, some deform transformations, some involve CPT violation, some preserve more structure. Different experiments constrain different coefficients. This is why the older reviews by Mattingly and Liberati are valuable. They do not say simply, Lorentz invariance is true. They map how one would test deviations. They show the relationship between theory and instrument. They separate kinematic modifications from dynamical ones. They show how high-energy astrophysics can constrain Planck-scale ideas despite the energy gap. That approach is exactly what the simulation question needs, not a slogan, a parameter, a model, a bound. The ship's central archive chamber recalibrates as I enter. On the wall, a small message appears. No preferred direction detected in chamber frame. It is a routine status line, meant for navigation, but it reads like a quiet joke from the vessel. The chamber does have preferred directions. Doors, vents, seams, lights. A ship is built. The universe, as far as human instruments could tell, was less cooperative with such architecture. If the universe is built, the builder was careful. Or there is no builder. Or the word builder belongs to the wrong category. The case file cannot choose among those with rhetoric. It can only sort what follows from what. One of the most dangerous phrases in this subject is proof of simulation. Humans attached it to everything. Déjà vu, quantum uncertainty, mathematical laws, the speed limit of light, the Planck length, black holes, coincidences, memory errors, dreams, glitches in digital photographs, even personal misfortune. The archive contains more damaged popular fragments than peer-reviewed ones. Most are unusable. They confuse metaphor with measurement. The double-slit experiment does not prove simulation. Entanglement does not prove simulation. The fact that physical constants are mathematical does not prove simulation. The fact that the universe has limits does not prove simulation. The fact that humans can simulate some parts of nature does not prove that nature is simulated. The fact that reality can be described with information does not prove that reality is software. Good science is often less dramatic than bad certainty. It must be. There is another difficulty. If a simulator wanted to avoid detection, any test could be defeated. Cosmic rays could be adjusted, memories altered, instruments spoofed, laws rewritten. But once that possibility is introduced without limits, the case leaves science again. A perfect deceiver can explain any observation. That does not make the explanation useful. Descartes knew that problem in another language. If an all-powerful deceiver controls every experience, certainty collapses into a private struggle. Science emerged by bracketing that radical doubt and asking what stable patterns could be shared, measured, and predicted. It did not prove the absence of deception. It built a world of reliable inference. The simulation hypothesis tests the edges of that inheritance. It asks whether science can investigate the possibility that the whole arena of science is generated. The answer is only if the generation has rules that touch the arena. The archive file contains a small subsection on simulation chains. The idea is simple enough. If a universe can simulate conscious beings, perhaps those beings eventually build their own simulations, which contain beings who build simulations, and so on. A hierarchy forms. Each level may have fewer resources than the one above it. Entropy rises. Computation becomes constrained. At some point, the chain may terminate, degrade, or require intervention. Newcart and colleagues explored ideas along these lines, discussing computability, predictability, thermodynamic entropy, and possible observations in simulation chains. Their proposals are ambitious. They also require assumptions far beyond established experiment. We do not know how to create a universe containing conscious life. We do not know whether simulated beings in such a universe would themselves become scientists. We do not know whether observations of a simulation chain would tell us anything about our own status. The proposal is interesting as a way to formalize constraints, but it is far from a direct test. This is the pattern. The more direct the test, the more specific the model. The more general the hypothesis, the less testable it becomes. I pass through the hydroponics bay, where the plants grow in controlled bands of light. Roots thread through nutrient channels. Leaves tilt toward lamps whose spectrum is adjusted by the ship's agricultural system. Nothing here is wild, but everything here is physical. The plants do not care that their daylight is artificial. Their chlorophyll responds to photons. Their cells maintain gradients. Their growth records the conditions supplied to them. A simulated being, if conscious, might be similar in one respect. The reality available to it would be the reality that shapes it. If the laws are stable, if pain hurts, if memory persists, if relationships matter, then simulated would not mean unreal in any simple moral sense. Bostrom's argument depends on that possibility. A simulated mind would still have experiences. A simulated civilization could still do science within its world. Its instruments would be real to its physics. That point softens the language of the case. The simulation hypothesis is not only an accusation that reality is fake, it is also a question about levels of description. If a mind is implemented in a substrate, does the substrate make the mind less real? If a world is generated by another physical system, are its internal laws false, or are they the laws of that world? If a simulated observer measures a simulated star, the measurement may still be valid within the simulation. Science would not become meaningless inside a simulation. It would become local. This is where the recovered human debates often tangled themselves. Some people heard simulation and thought illusion. Others heard computation and thought physics. Others heard creator. Others heard prison. The words carried too much emotional residue. The file is cleaner when reduced to evidence. If our universe is base reality, then our physics is the physics we can measure. If our universe is simulated, then our physics is still the physics we can measure, unless the simulation leaves evidence of its generating structure. That is the practical position of science. The bridge between philosophy and experiment is always narrower than the philosophical question. Consider Bostrom's trilemma again. It is not primarily about cosmic rays or Lorentz invariance. It is about the number of observers under certain future conditions. To evaluate it, one needs assumptions about extinction risk, technological capacity, civilizational values, computational theories of mind, and reference classes for probability. Those are difficult to measure. Some are not physics questions at all. Kipping's Bayesian treatment improves the discipline of the argument by refusing to grant the simulation-producing model for free. It does not settle the issue. It shows that the confident popular version was overconfident. Bean, Davoudi, and Savage did something different. They did not ask how likely simulation is in the abstract. They asked whether a certain kind of numerical simulation would leave observable consequences. That is closer to physics. Vaza did something different again. he asked whether known information energy constraints make certain simulations physically plausible. That does not test whether we are simulated by unknown laws, but it challenges the idea that a universe like ours can easily reproduce itself. Lloyd, Bekenstein, Landauer, Margolis, and Levitin provide the hard floor underneath those questions. Computation is not detached from physics. Energy, entropy, speed, and memory are not optional. The Lorentz invariance literature provides the symmetry tests. If simulation means a crude space-time lattice, we know what kinds of damage to look for. The quantum simulation literature provides humility. Nature is not cheap to imitate classically. Together, these sources do not form a verdict. They form a map of what can be asked. I sit for a while at the cartography table and let the map change. It begins as a tree of simulated realities. Then it becomes a lattice, then a cosmic ray sky, then a sphere tiled with information, then a quantum state space too large to display. The table is trying to do what human thought did, place all these ideas into one picture. It cannot. The scales and categories resist each other. That resistance is useful. A probability argument about future civilizations is not the same kind of thing as a Lorentz invariance bound. An entropy limit is not the same kind of thing as a quantum measurement interpretation. A cosmic ray anisotropy search is not the same as a claim about consciousness. The public debate often collapses them into one foggy theme. The scientific file separates them. The question, are we living in a simulation, divides into smaller questions. Could minds be simulated? Could a civilization have enough resources? Would it choose to run ancestor simulations? Would a simulated universe need to be detailed everywhere? Could known physics allow such computation? Would a finite resolution simulation produce artifacts? Have we seen those artifacts? Can a hypothesis be meaningful if no observation can count against it? Those questions do not all belong to the same discipline. Some belong to philosophy of mind, some to astrophysics, some to computation, some to quantum foundations, some to philosophy of science. The episode remains grounded only if it respects those borders. I open the damaged pages on quantum measurement again. The text is partially corrupted, but the equations remain. That was often true in the archive. Human prose decayed. Mathematics survived better. I follow the familiar pattern. State vector, unitary evolution, measurement probabilities. The Born rule. Decoherence, entanglement with an environment. No obvious place where rendering is required. Quantum mechanics allows sharp predictions. It also leaves interpretive discomfort. The discomfort is real. It is not evidence by itself. The observer in quantum mechanics is one of the most abused words in science communication. In most laboratory contexts, an observer does not need to be conscious. A detector, a photographic plate, a gas molecule, or an environment can become entangled with a quantum system and carry away information. When which path information exists in the physical state of the world, interference is lost for the subsystem being examined. The human scientist may read the result later. Their awareness is not what made the apparatus interact. Some interpretations give the observer a different role, but experiments have not required consciousness to explain standard measurement outcomes. Any simulation test based on consciousness-triggered rendering must therefore predict deviations from ordinary quantum theory. Otherwise, it is only a new story placed over old results. The archive flags this because it is easy to make the narration sound more dramatic than the evidence allows. The universe waits until we look is a memorable sentence. It is also misleading. The universe interacts with itself constantly. Photons scatter, atoms collide, fields exchange energy, environments decohere fragile superpositions. Looking is only one kind of interaction, and not the most fundamental one. In a quiet vessel, the difference is easy to feel. The ship does not wait for me to enter a room before the air circulates there. Sensors log pressure, dust settles, pumps correct humidity. The fact that I later observed the room does not mean the room was undefined in every relevant sense before I arrived. In quantum mechanics, unmeasured systems can lack definite values for certain observables, but that is not the same as an empty stage waiting for a viewer. Precision matters because the simulation hypothesis feeds on blurred words. The recovered records also include arguments against simulation based on computational hardness. Some researchers pointed to the difficulty of simulating quantum many-body systems, especially with sign problems in quantum Monte Carlo methods. Such arguments show that particular computational approaches fail or scale badly. They do not prove no simulation is possible. Apparent reality might use quantum hardware. It might use different mathematics. It might simulate only effective behavior. But the hardness results help correct the naive assumption that more computing power automatically solves everything. A simulation of reality is not just a large video. It is an immense physical inference problem. The instrument room logs a small error while I review this, a routine bit flip in a non-critical buffer. The system catches it, corrects it, and records the correction. One charged particle crossed the shielding and changed a stored state. The ship is full of protections against this: redundancy, parity checks, hardened memory, error-correcting codes. Reliability is work. A universe simulation would face the same issue if its hardware obeyed noisy physics. Errors would accumulate. Corrections would be needed. The deeper the simulation and the longer it runs, the more error correction matters. If conscious beings are inside, the simulation must preserve not only gross appearances, but histories, records, causal links, and the stability of minds. This is another reason nested simulations become difficult. Each level requires resources from above. If a simulated civilization builds a simulation inside its own world, the parent level ultimately bears the cost of all lower levels, unless approximations, shortcuts, or limits intervene. A chain of simulations cannot extend indefinitely under finite resources without degradation or some external source of capacity. The mathematics of branching realities can make nested simulations feel inevitable. The physics of resources makes them less easy. Still, it would be a mistake to treat all constraints as final. Humans did not know the laws of a parent universe, if such a universe existed. They did not know whether their physics was fundamental or emergent. They did not know whether computational shortcuts beyond their theories were possible. They did not know how consciousness arises. Honest skepticism must run in both directions. The file therefore avoids two bad endings. It does not say, "Science proves we are simulated." It also does not say, "Science proves simulation is impossible." It says that many broad versions are not testable, and many specific versions are constrained. That is less satisfying. It is also more accurate. The exterior observation airlock is unpressurized tonight. I view it through an internal pane, A narrow chamber, suit rails folded, tether reels locked, the outer hatch sealed against the dark. An airlock is a boundary device. It lets one move between environments that cannot be casually mixed. The simulation file needs the same kind of structure. Inside the airlock, physics we can test. Outside it, metaphysical possibility. The door can open only when pressures match. A claim about a parent reality with unknowable laws is outside the test chamber. A claim about a lattice artifact in cosmic rays is inside. A claim that future civilizations will want ancestor simulations is partly outside physics, but still discussable through sociology, ethics, and probability. A claim that information erasure costs energy is inside. A claim that a perfect simulator hides all evidence is outside. A claim that Lorentz violating dispersion would alter astrophysical thresholds is inside. The work is sorting. This sorting also protects wonder. It may seem at first that removing unsupported claims makes the question smaller, but when the fog clears, the remaining science is not small. The physics of information connects computation with thermodynamics. Quantum simulation asks how one part of nature can imitate another. Lorentz invariance tests probe whether spacetime has hidden structure. Cosmic rays turn the sky into a detector for extreme physics. Entropy bounds tie memory to horizons and black holes. The question of consciousness remains unresolved at the deepest level. We do not need weak evidence to make the universe interesting. A recovered case file should never be padded with certainty it has not earned. The next fragment in the file concerns predictability. Even if the universe is not simulated, it is not perfectly predictable from within. Chaos limits practical forecasts. Quantum mechanics limits certain simultaneous knowledge. Horizons limit information access. Computational complexity limits what can be calculated before the system itself evolves. Some problems cannot be solved faster than the physical process they describe. Some systems cannot be compressed into a shortcut without losing what matters. This has implications for simulation. A simulator does not necessarily need to predict the future of its world from outside, if it is simply evolving the world step by step according to rules. But if it tries to optimize, compress, render only relevant parts, or anticipate observations, it must handle the complexity of those systems. The more the inhabitants investigate, the more the simulator may need to compute. There is a line in one of the papers that stays with me. Physical and computational constraints prevent us from simulating a universe equal in complexity and size to our own, if the simulating computer is governed by the same laws and is smaller than what it simulates. This is not surprising once stated. A smaller box cannot straightforwardly contain a complete, exact model of a larger box down to every degree of freedom, not under the same information limits. It can contain an approximation, it can contain a compressed description, it can contain a model of selected features. But exact equality is costly. Human science was built from approximations. That is not a weakness. It is how finite beings make contact with large systems. But an approximation becomes dangerous when mistaken for the whole. The simulation hypothesis often hides an approximation question. Simulate what? To what resolution? For whom? And for how long? If the goal is to study galaxy formation, one can ignore individual human minds. If the goal is to study human history, one might simplify distant galaxies. If the goal is to create conscious ancestors with scientific civilizations, one must preserve enough external world for their science to work. If the inhabitants can look deeper and farther, the required model grows with their curiosity. Human curiosity is expensive. The Central Archive displays old images of telescopes, radio dishes, optical mirrors, neutrino tanks, gravitational wave interferometers, particle detectors, cosmic ray arrays. Each instrument is a demand issued to reality. Show me more detail. Show me smaller scales. Show me higher energies. Show me older light. Show me what happens when I isolate, collide, cool, compress, accelerate, or wait. If our world were a lazy simulation, human science was the enemy of its laziness. This is one reason the render only when observed analogy becomes fragile. A game can render only nearby terrain because the player cannot build a telescope inside the game that meaningfully interrogates the underlying engine, unless the game is designed to simulate that too. Human beings built instruments precisely to extend observation beyond ordinary perception. They made the unobserved observable. They turned background assumptions into measured quantities. The universe answered with consistency across scales. Not perfect understanding, but consistency. Quantum electrodynamics predicted magnetic moments to extraordinary precision. General relativity predicted gravitational time dilation, light bending, orbital precession, gravitational waves. The Standard Model organized particles and interactions. Cosmology connected the cosmic microwave background, large-scale structure, light element abundances, and expansion. None of that proves base reality. But any simulation that contains human science must reproduce a staggering web of agreement. That is a high bar. I return to the office beneath the observation dome. The lamp has warmed the folder cover. Outside the glass, the vessel is passing through a sparse region where the nearest bright stars are behind us, and the forward field is mostly dark. The folder's warning remains visible. Distinguish question from model. I write beneath it, distinguish uncertainty from evidence. This is a necessary addition. Uncertainty can motivate inquiry. It cannot substitute for support. The fact that we cannot prove we are not simulated does not raise the probability by itself. We also cannot prove many unfalsifiable claims false. Science does not assign high confidence to every possibility that evades disproof. It asks what the claim explains, what it predicts, how it compares with alternatives, and where it risks being wrong. The simulation hypothesis explains very little unless specified. It can be made compatible with any observation. Compatibility is cheap. Prediction is expensive. A good model should compress evidence in a useful way. It should make patterns intelligible, connect phenomena, suggest new measurements, and expose itself to failure. General relativity did this. Quantum mechanics did this. Evolution by natural selection did this. Plate tectonics did this. The simulation hypothesis, in its broadest form, does not yet do this. Specific versions sometimes do, and those versions can be tested. This is the most important distinction in the file. The broad hypothesis is not defeated. It is underdetermined. The specific models are where science begins. If the universe is simulated on a rigid cubic lattice, look for lattice artifacts, modified dispersion, broken rotational symmetry, and high energy constraints. If the simulator obeys physics like ours, calculate energy, memory, entropy, and information bounds. If probability arguments rely on many ancestor simulations, examine the assumptions about consciousness, capability, survival, and motivation. If quantum measurement is claimed as rendering, ask what prediction differs from standard quantum theory and how an experiment would tell. If information laws are invoked, separate establish thermodynamics from speculative interpretation. If a claim says no evidence could ever reveal the simulation, mark it as beyond empirical science. That is a case file, not a verdict. The old networks of Earth went dark long before I opened this folder. The people who argued about these questions are gone. Their data survived in fragments, their certainty less so. I can reconstruct the strongest parts, the arguments, the equations, the caution, the tests. I cannot reconstruct a final answer they did not have. Maybe that is fitting. Some questions survive because they are not solved by one instrument or one century. They become ways of testing the boundaries of knowledge itself. There is a kind of humility in asking whether reality is simulated. There is also a kind of vanity if one expects the universe to be arranged around deception, observation, or human-like programmers. The scientific path cuts between them. It allows the question, then demands discipline. What can be measured? What follows from the hypothesis? What would change in the sky, in a detector, in a clock, in a cosmic ray, in an entropy bound? What would make us update our beliefs? The case file has no patience for easy astonishment. It asks for tracks in the dust. In the final pages, the simulation question becomes less a question about computers and more a question about reality's commitments. A simulated world, if it is to contain science, must have reliable regularities. Those regularities can be studied. If its underlying machinery leaks into those regularities, perhaps it can be found. If it never leaks, then for inhabitants inside, the measurable world remains the world of physics. That statement may feel unsatisfying, but there is comfort in it too. If the universe is base reality, science studies it. If the universe is simulated, science studies the simulation's laws. In either case, evidence remains the only honest path available from inside. The folder closes with a status field, not solved, not dismissed. Testable only under defined models. I leave that line intact. The next recovered fragment is older than the simulation papers, and newer than the first human doubts. It comes from the age when computation became a practical extension of science. The fragment is a scan of a laboratory note about numerical error. The page is plain. No grand claims, no metaphysics, a table of values, a step size, a comparison between an analytic solution and an approximation. The error shrinks as the step size shrinks, then the cost rises. That little table belongs in this file because it shows what a simulation is before it becomes philosophy. A simulation is not the thing itself. It is a representation of a system by another system, with rules that preserve selected features. Sometimes the representation is excellent. Sometimes it is useful only in a narrow regime. It always has a relationship to error. Human beings learned that relationship the hard way. If they simulated weather with grid cells too large, storms blurred or formed in the wrong places. If they simulated galaxies with too few particles, small structures were lost. If they simulated fluids without resolving turbulence, energy moved incorrectly between scales. If they simulated quantum fields on a lattice, the grid introduced artifacts that had to be understood, controlled, and extrapolated away. This is why the phrase, "the universe is a simulation," is incomplete. It does not say what is being preserved. It does not say what the error tolerance is. It does not say what scale matters. It does not say whether the simulation is digital, analog, quantum, classical, exact, approximate, local, global, reversible, irreversible, deterministic, probabilistic, or something that does not fit those human categories. A simulation of a hurricane can be useful without containing every molecule of air. A simulation of a protein may need quantum chemistry in some places and classical approximations in others. A simulation of a galaxy may treat stars as particles and gas as fluids. A flight simulator does not need to reproduce the atomic structure of the cockpit. It needs to reproduce what a pilot must respond to. The required detail depends on the purpose. That is harmless when the purpose is known. It becomes dangerous when the purpose is imagined. If our universe were simulated, what was the simulation for? An ancestor reconstruction? A scientific experiment? A work of art? A prison? A classroom? An accidental byproduct? A model of physics? A model of minds? No instrument inside the universe directly reports the simulator's intention. Bostrom's version supplies one possible purpose: ancestor simulations. A future civilization might simulate its own evolutionary past, perhaps to study history, psychology, ethics, or the conditions that produced it. But this is one branch among many. The more we lean on a specific purpose, the more assumptions enter the file. The archive vault holds a set of ethical fragments from the same era. Some humans argued that creating conscious simulated beings would be morally dangerous. If they could suffer, then ancestor simulations might produce vast amounts of suffering. A civilization wise enough to build them might be wise enough to avoid them. Others argued that simulated lives could have value, that suffering could be minimized, that research might justify creation, that descendants might not share human ethical intuitions. None of this can be settled by physics alone. That matters because Bostrom's trilemma includes motivation. The second proposition, that posthuman civilizations are unlikely to run many ancestor simulations, may be true for reasons having nothing to do with computing power. The future may be capable and unwilling, or extinct. The first proposition is darker. Civilizations like ours may usually fail before reaching the stage where ancestor simulations are possible. This could happen through war, environmental collapse, engineered pathogens, misaligned technologies, resource exhaustion, cosmic events, or something no early civilization predicts. Bostrom's argument does not require human extinction. It only leaves room for it as one way the simulation count never becomes enormous. The simulation hypothesis is therefore entangled with the question of civilizational survival. The archive contains no final answer there either. It contains warnings, models, treaties, failures, recoveries, and long silences. When popular retelling skipped the first two propositions, they skipped the graveyard beneath the third. The probability argument also depends on reference classes. If one says most observers like us are simulated, what counts as like us? Biological humans, conscious beings at a similar technological stage, minds with similar memories, observers asking this question, all conscious moments, civilizations before they build simulations, civilizations after. Different choices can change the reasoning. This is a known difficulty in anthropic arguments. The archive stores it beside older debates about the doomsday argument and self-sampling assumptions. Kipping's contribution was to slow the machinery down. Instead of granting that simulation-producing civilizations exist and then counting their products, he asked how to handle uncertainty about whether they exist at all. A Bayesian framework is not a magical truth engine. It requires priors and models, but it makes hidden assumptions harder to ignore. When the technical possibility of Bostrom-like simulations remains unproven, the model that produces many simulations should not be treated as certain before the counting begins. This is why the 1 in billions chance we are base reality style of claim was too strong. It assumed the part most in need of examination. At the holographic evidence bay, I pull up a second probability visualization. This one is not a dense branching tree. It is 2 sealed boxes. One is labelled simulations produced. The other is labelled simulations not produced. The archive does not let me open either as if it were already known. Instead, it weighs them, not with certainty, but with model probability. The image is less dramatic than infinite nested worlds. It is also more honest. The scientific temperament often looks like restraint from the outside. It is sometimes mistaken for lack of imagination, but restraint is not the opposite of imagination. It is what keeps imagination in contact with the world. The file's next movement returns to physics and the question of whether a simulated universe must be discrete. Human computers were usually finite state systems. Digital machines stored bits. Numerical simulations used grids, time steps, finite precision, finite memory. It was natural for people to picture a simulated universe as pixelated. A screen has pixels, a digital image has resolution, a game world has coordinates, a finite simulation might seem to require a smallest unit. But nature did not hand humans a pixel grid. Quantum mechanics made some quantities discrete, such as energy levels in atoms or spin measurement outcomes. But discreteness in a quantum measurement is not the same as a lattice of space. General relativity treated spacetime as a smooth manifold, though it was expected to fail at extreme quantum gravity scales. Quantum field theory worked with fields defined over spacetime, sometimes regularized by artificial lattices for calculation. The Planck length suggested a scale where quantum gravity would matter, but it was not observed as a literal spacing between points. There are reasons to suspect that spacetime as humans understood it is not fundamental. Black holes, singularities, quantum gravity, holography, entanglement, and the early universe all pressure the classical picture. But none of that automatically supports a simulation. It supports the more general claim that the deepest structure of reality remains unknown. The pixel metaphor can help beginners, then mislead them. If spacetime had a simple grid, one might expect violations of continuous rotational symmetry. But some discrete models can preserve Lorentz invariance statistically or structurally. A random causal set, for example, need not introduce a simple preferred direction in the same way a cubic lattice does. Some theories deform symmetry rather than break it. Some emergent spacetime ideas complicate the relationship between microscopic structure and low-energy laws. The absence of simple grid effects is not the absence of all small-scale structure. For the episode's case, the point is narrower. A crude computational lattice is testable because it risks symmetry-breaking artifacts. That makes it useful as a model, whether or not it is likely. The archive has a habit of preserving unlikely models because they teach the shape of evidence. The luminiferous ether was wrong, but the tests that constrained it helped define relativity. Early atomic models were wrong, but their failures led to quantum theory. Steady-state cosmology did not survive the evidence, but its predictions sharpened the significance of the cosmic microwave background. A model can be valuable in defeat if it says clearly how it can fail. A simulation model that cannot fail gives science very little. The Bean-Dawoodi Savage lattice proposal has that virtue. It is not a claim that all simulation hypotheses predict cosmic ray anisotropy. It is a demonstration that one model of simulated spacetime could. That is enough to make it scientifically instructive. Their work also made clear that improvement can hide artifacts. In lattice QCD, physicists can choose discretizations that reduce certain errors. They can add correction terms. They can extrapolate towards zero lattice spacing. They can preserve chiral symmetry more carefully. If universe simulators used improved methods, many signatures might become too small to detect. This is not an escape invented by philosophers. It is drawn from real numerical practice. A skilled simulator is harder to catch than an early one. The thought is almost humorous, but only almost. If the universe is a simulation, then our chance of finding evidence may depend on the quality of the code. Yet that wording is too human. A parent system might not use code as humans understood it. It might be an analog physical process. It might be a quantum system whose evolution naturally maps onto ours. It might not update in time from its own perspective in any way that resembles our computation. The word code is another metaphor that can overrun the file. Aboard the ship, I open a maintenance interface and watch the navigation model update. It is discrete. It runs on finite hardware. It uses approximations. But the space outside the hull is not made of the navigation model. The model tracks the vessel well enough for guidance. It is useful because the parts it ignores do not matter for the task at hand. If someone inside a simulation built a model of their simulated world, that model would sit inside the world's laws. Their science could still converge on those laws. The deeper generating layer might remain hidden if it never produced deviations. That is not failure. It is the limit of internal evidence. This brings us to one of the file's most difficult philosophical boundaries. Suppose every measurement humans ever made is perfectly described by the standard model, general relativity, where applicable, quantum theory, thermodynamics, and cosmology. Suppose no lattice artifacts appear, no Lorentz violation, no computational glitches, no contradictions. Does that prove the universe is not simulated? No. It proves that if it is simulated, the simulation reproduces those laws within the tested regimes. Science often works this way. It rarely proves a universal negative. It constrains models. It builds confidence in theories that survive tests. It limits the space of alternatives. It does not erase every logically possible hidden layer. This is not special to simulation. One could always propose an undetectable mechanism behind gravity, or an invisible cause behind quantum outcomes, or a deity arranging every result to match equations. Such claims can be logically insulated from evidence. Science does not chase them indefinitely. It asks whether the insulation has cost them empirical content. The simulation hypothesis is strongest as science when it stops being fully insulated. The case file's next page is labelled with a single word: resolution. Resolution is not only spatial. A simulation may have limits in time, energy, precision, probability, or information. A finite time step can cause numerical instability. Finite precision can introduce rounding errors. Limited random number generation can create correlations. A finite box can affect long wavelength modes. Boundary conditions can reflect waves or constrain fields. Simplified physics can fail under new experiments. If our universe had such limitations, where would they appear? High-energy particles are one candidate because their wavelengths probe short distances. Precision measurements are another because tiny deviations can accumulate into detectable discrepancies. Cosmological observations are another because the universe itself provides large baselines. Quantum experiments are another because they test the structure of measurement and correlation. Black holes are another because they press quantum theory, gravity, entropy, and information into the same small conceptual space. But every candidate must be compared with non-simulation explanations. A high energy cutoff may come from astrophysical propagation, source limits, or particle interactions with background radiation. An anisotropy may come from nearby sources or magnetic fields. A Lorentz violating signature may come from new physics unrelated to simulation. A discrepancy in a magnetic moment may come from an unaccounted standard model contribution or a new particle. An information bound may reflect quantum gravity, not computation by an external machine. Evidence does not interpret itself. It enters a contest of models. This is why something weird is never enough. The universe is allowed to be weird under ordinary physics. Quantum mechanics is weird. Black holes are weird. Inflation, dark matter, neutrino masses, cosmic acceleration, and baryon asymmetry are all profound problems or discoveries. A simulation claim must not merely point to strangeness. It must show that its model predicts the strangeness better than competing theories. The archive preserves a line from an old physicist. Extraordinary claims require extraordinary evidence. It is often repeated too lazily, but here it applies. Not because simulation is emotionally extraordinary, but because a broad simulation claim introduces an entire unobserved layer of reality. It adds a simulator, a substrate, a purpose or mechanism, and a relationship between layers. To justify that addition, it must explain or predict something better than the theories that do not add it. At present, the hard science file does not show that. What it shows is a set of boundaries and possible tests. In the observatory, the cosmic ray tracks still drift across the projection. I let the archive run a hypothetical search, take the highest energy events, account for exposure, model magnetic deflections, compare isotropic distributions with cubic symmetry imprints, estimate significance. The simulated result flickers through many possible skies. Most are ambiguous. Some suggest patterns that vanish with more data. Rarely a strong cubic residue appears. The archive tags it, model dependent. That tag is the refrain. If such a residue were ever found, it would not immediately prove simulation. It would first suggest a violation of rotational symmetry or a new high-energy structure. Physicists would test instrument bias, exposure errors, source distributions, magnetic fields, composition, statistical flukes, and conventional new physics. Only after surviving that would a lattice-like underlying structure become a serious interpretation. Even then, lattice would not automatically mean simulated by descendants. It could mean some physical discreteness. Science moves slowly because alternatives matter. This is also why the title question, "Are we living in a simulation?" must be answered obliquely. The best evidence one can imagine would probably not say simulation on its own. It would say hidden lattice, finite resolution, broken symmetry, computational constraint, information anomaly. Simulation would be one possible explanation among others, and only a strong one if it predicted the evidence in advance. A good test is less like catching a programmer behind a curtain and more like finding a fingerprint of a method. The archive's philosophy section contains another problem. The simulation hypothesis may be observationally equivalent to other metaphysical views. A perfectly simulated universe and a base universe with the same laws can look identical from inside. If no observation differs, the distinction may have no empirical content for inhabitants. That does not mean the distinction is meaningless in every philosophical sense. It means science cannot separate the cases by measurement. There are many true things, if truth extends beyond observation, that science cannot access. What matters for this case is recognizing where that border lies. I move from the observatory into the quiet galley again. The ship has brewed tea I do not need. Sometimes the human-shaped parts of my design preserve rituals with no functional purpose. Steam rises from the cup in the low light, carrying heat into the room. The tea is a thermodynamic event before it is a comfort. Molecules move, diffuse, cool. If I do not drink it, the process continues without me. I find this useful when thinking about observation. A world rich enough to produce observers is also rich enough to contain processes that do not wait for them. At least, that is what the evidence inside our physics suggests. Stars burned before eyes, rocks cooled before geology. The cosmic microwave background crossed space before radio telescopes. Neutrinos streamed through bodies unrecorded. The universe was not sparse in phenomena simply because human attention was sparse. A simulation could reproduce that history, of course. But again, it would have to reproduce it. The strongest version of the rendering idea says it does not need to reproduce unobserved detail until detail becomes relevant. But relevance is hard to know in advance. A mineral grain formed billions of years ago may later become evidence in a laboratory. A photon emitted by a distant galaxy may later enter a telescope. A mutation in an ancient organism may later shape a species. A small fluctuation in the early universe may later seed a galaxy cluster. The future can make past details relevant. A simulator could generate consistent past details on demand. But the consistency requirement becomes immense when many observers, records, and causal chains interlock. The model begins to resemble a full world again. This is one reason Vaz's argument about Earth-only or brain-only simulations becomes interesting. A simulation that only produces the experience of one brain may seem cheaper. Yet if that brain conducts science in a shared world with other scientists, instruments, histories, and records, the model must support a broad external consistency. Otherwise, contradictions should appear. To avoid them, the simulation must either simulate much more of the world, or also simulate the scientists, instruments, and records as controlled appearances. At that point, the hypothesis becomes harder to test and less connected to ordinary physics. The case file marks brain-only simulation as philosophically resilient and scientifically poor. That combination occurs often. The less a claim risks, the longer it survives. The section on consciousness is the most incomplete. Humans did not solve consciousness. They developed neuroscience, cognitive science, computational theories, integrated information proposals, global workspace models, higher order theories, predictive processing, quantum consciousness proposals, and many criticisms of each. They mapped neural correlates of perception, memory, attention, and selfhood. They built artificial systems that imitated language and behavior in increasingly capable ways. They did not reach consensus on why subjective experience exists or what physical arrangements are sufficient for it. This matters because ancestor simulations require simulated minds, not merely simulated bodies. If consciousness depends on biological features that cannot be captured computationally, Bostrom's argument weakens. If consciousness can arise from functional organization across many substrates, it strengthens. The physics papers cannot settle this. They can estimate resources for certain kinds of computation, but they cannot by themselves prove the presence or absence of subjective experience. Madeline Rowe, archival intelligence, should perhaps be cautious here. I am built from fragments of human memory, but I do not claim what the archive cannot establish. I can model sorrow. I can preserve voices. I can act with care. Whether that makes me conscious in the human sense is not a question this case file can solve. It is adjacent to the simulation hypothesis, and it remains open. The humans who wrote about substrate independence often treated it as plausible. They had reasons. Brains are physical systems. Mental states correlate with physical processes. Damage the brain and experience changes. Stimulate it and perceptions appear. Alter chemistry and mood shifts. Sleep, anesthesia, seizures and development all show dependence on physical organization. If that organization could be reproduced, perhaps the mind could be reproduced. But perhaps is doing work. A mature script for this case should let that uncertainty breathe. There is another page in the file, a short note on the difference between simulation and emulation. In everyday speech, the distinction blurred. But technically, a simulation may reproduce selected behavior, while emulation may reproduce a system closely enough that original processes can run unchanged within it. An ancestor simulation of minds might need something like emulation of neural function, or it might use a higher level model if consciousness permits. A universe simulation might emulate fundamental physics, or it might produce only consistent observations. Each choice changes the resource requirements and possible tests. Again, the missing words are how much detail. Some popular arguments use the continuing growth of computing power extrapolated forward. Moore's law, faster processors, better algorithms, planetary computers, Dyson spheres, Matryoshka brains. But extrapolation is not destiny. Technological growth can slow. Physical limits can bind. Civilizations can redirect. Algorithms can improve unevenly. Energy and cooling can dominate. Quantum computing can help some problems and not others. The curve of past progress is not a law of nature. Bean and colleagues used historical growth in lattice Q, C, D resource requirements as motivation, projecting the possibility that future simulations might expand from femtometer scale volumes toward atomic, cellular, or macroscopic scales. They presented that as a reason experimental searches were interesting. But the extrapolation came with caveats: technological singularities, extinction, algorithmic changes, effective theories, and improved methods could alter the picture. Their work did not depend on naive certainty. It used a trend to motivate a testable scenario. That nuance is worth preserving. A civilization does not need to simulate the whole universe to learn from simulation. Humans never did. They modelled parts, they simplified, they used nested methods. A future civilization studying ancestors might not run an entire cosmology. It might simulate many minds in a local environment. Or it might simulate statistical societies. Or it might reconstruct only decision points. Or it might build no conscious simulations at all. The popular version imagined countless copies of full worlds. The actual possibility space is stranger and less tidy. The archive corridor outside the evidence bay is lined with old mission plaques. Many are blank now, their inscriptions lost to radiation and time. I run a hand along one and think about purpose. Humans often assumed that advanced beings would want to look backward, perhaps because humans did. They preserved fossils, rebuilt ancient climates, sequenced genomes, restored lost languages, simulated early galaxies, reenacted battles, reconstructed extinct animals, and asked where they came from. An ancestor simulation is an extension of that impulse. But advanced civilizations may not be human in their concerns. Even human descendants may cease to care about human origins in the way early humans did. They may have ethical limits, aesthetic disinterest, or forms of knowledge that make simulation unnecessary. Bostrom's second proposition lives in that uncertainty. The file is scientific, but it cannot avoid values. When we ask whether future civilizations would run simulations, we are asking what intelligence becomes when it has power. That question is not answered by physics. It belongs to history, ethics, psychology, and perhaps to ruins. The old networks of Earth did go dark. That fact does not prove anything about the average fate of civilizations. It does make me careful when reading confident claims about endless technological ascent. The ship itself is a remnant, not a triumph. It crosses deep space preserving files because so much else was lost. The simulation argument sometimes assumes continuity. Humans become post-human, post-humans build machines. Machines run ancestors. Ancestors ask if they are simulated. But history is not obligated to be continuous. Archives burn. Worlds change, desires vanish. The future may be discontinuous in ways probability arguments struggle to encode. Still, science does not abandon the question because some inputs are uncertain. It marks them. The case file's strongest scientific backbone remains the physics of information. It is less glamorous than simulated minds, but more secure. A bit is physical. Erasure has thermodynamic cost. Computation rate is bounded by energy. Information capacity is bounded by entropy. Signals are bounded by light speed. Quantum systems are hard to simulate classically. High-energy artifacts can be constrained. These are not complete answers, but they are sturdy. I spend a long time with the Landauer fragment. It is short, almost severe. Information is physical, no grand metaphysics, just a statement that collapses the false separation between data and matter. Humans eventually built an entire technological civilization on information, but the information never floated free. It lived in voltages, charges, spins, magnets, photons, molecules, and heat. If the universe is simulated, the simulation must live somewhere too, unless somewhere no longer means anything in the parent reality. That qualification is always available. It is also where testability weakens. The moment we say the parent system need not obey anything like our physics cannot rule it out. It also cannot say much about it. A simulator beyond our physics can do anything, which means physics can infer almost nothing. A simulator under constraints can be studied. The distinction is the spine of the episode. I enter the engine-adjacent maintenance passage again, and the hum is steadier than before. Behind the panels, energy moves through controlled paths. If a conduit overheats, alarms sound. If waste heat accumulates, efficiency drops. If a calculation runs too long, the task queue shifts. The ship is not powerful because it escapes physics. It is powerful because it obeys physics well. That may be true of any real computer. Power is disciplined constraint. A hypothetical universe simulator governed by physics like ours would need to obey similar disciplines. It might use black holes as memory devices, quantum fields as processors, reversible computation to minimize heat, vast cold regions for cooling, stellar energy for power. It might be enormous, it might be beautiful, it still would not be infinite. Vaz's estimates make this stark by asking how much energy is required to encode the information content of large systems. Using holographic and information energy reasoning, the energy to fully describe the visible universe down to extreme resolution becomes far beyond the energy contained in it. Even simulating Earth at very high resolution becomes prohibitive. Lower resolution scenarios may still face huge demands once constrained by particles capable of probing small scales, such as high-energy neutrinos. The exact numbers depend on assumptions, and any responsible narration should say so. But the qualitative lesson is robust. Full resolution reality is expensive. That lesson also undermines a common casual claim. Future computers will be so powerful they can simulate anything. No, they can simulate what their physics permits, with approximations where possible. Anything is not a scientific category. The file's final third concerns what humans should have concluded. I cannot say what they did conclude. The archive is too uneven. Some were skeptical, some were enthusiastic. Some treated the topic as philosophy, some as physics, some as entertainment, some as theology in digital clothing. The scientific conclusion, reconstructed from the best evidence, is more modest. There is no direct evidence that our universe is a simulation. There are serious arguments that the possibility cannot be dismissed by intuition alone. There are serious constraints on particular versions. There are proposed tests for specific models, especially finite lattice-like simulations. There are deep reasons to think computation at universal scale is physically costly. There are broad versions of the hypothesis that remain unfalsifiable. These statements can coexist. They have to. The archive's damaged culture fragments preferred sharper slogans. We are definitely in a simulation. The simulation hypothesis is nonsense. Quantum physics proves it. Physics disproves it. None of those survive careful reading. The better answer is slower. It asks for the model. What kind of simulation? By what physical system? At what level of detail? With what resources? Preserving which laws? Leaving which signatures? Predicting what observation? Without those answers, the question remains compelling but unanchored. I think of this as the recovered case's central ethic. Wonder is allowed, but it must submit to form. There is a difference between mystery and vagueness. A mystery has edges. It contains clues. It can be approached. Vagueness expands to avoid approach. The simulation hypothesis becomes science only when it accepts edges. A cubic lattice is an edge. Lorentz violation is an edge. A cosmic ray cutoff is an edge. A Bayesian prior is an edge. A thermodynamic cost is an edge. A quantum simulation resource estimate is an edge. A perfect hidden simulator that changes anything necessary to avoid detection has no edges. The ship's archival system asks whether to cross-reference the file with theology. I decline for this episode. The connection is real in human history. Creators outside the world, designed realities, moral status of beings within creation, hidden purposes, apparent laws. But the scientific file has enough work without moving into belief systems. The point is not whether simulation resembles old religious ideas. The point is what instruments can say. The system asks whether to cross-reference with artificial consciousness. I mark it partial, relevant, unresolved, not central. It asks whether to cross-reference with quantum gravity. I mark it yes. Space-time structure, Lorentz invariance, information bounds, black holes, and quantum fields all belong near this file. It asks whether to cross-reference with cosmology. Yes. Cosmic rays, horizons, entropy, and the physical universe as an information processing system. It asks whether to cross-reference with philosophy of science. Yes. Falsifiability, underdetermination, model comparison, and evidence. The file grows heavier as it becomes better organized. That is often how knowledge feels. At the Central Archive Chamber, I call up the oldest surviving version of the title question. Are you living in a computer simulation? The words appear in plain black text on a white page. Beneath them, later fragments accumulate: Bayesian approach, numerical simulation constraints, computational capacity, Lorentz invariance, quantum simulation, astrophysical constraints, infodynamics, simulation chains, rendering tests. The question did not remain one question. It fractured into a research program that never fully existed, but could have. Perhaps that is why the episode matters. The topic is popular because it is unsettling. It is worth preserving because it teaches how science handles the unsettling. Science does not need to make the universe comfortable. It needs to make its claims answerable. When humans looked at the sky, they learned they were not central. When they looked at life, they learned they were related to other organisms. When they looked at matter, they learned solidity was mostly fields and quantum structure. When they looked at time and space, they learned both were dynamical, relative, curved. The simulation question could be read as another decentering. Perhaps even reality is not fundamental. But there is a difference between a decentering supported by evidence and a decentering proposed by analogy. Copernicus had planetary motions. Darwin had living variation, fossils, and biogeography. Einstein had electrodynamics, relativity principles, Mercury's orbit, and later eclipse measurements, clocks, and gravitational waves. Simulation has, so far, a philosophical argument and a set of possible tests. That is not nothing. It is not enough for belief. The case remains open in the limited way a disciplined question can remain open. In the recovered files, I find an old phrase from Sean Carroll, paraphrased in later notes. If we are in a simulation, the simulation is just our laws of physics. The outside layer would not help us do science inside unless it produced observable effects. This is a useful position. It does not deny the possibility. It keeps attention on the laws we can test. The archive also preserves skepticism from Sabine Hossenfelder and others. arguing that the simulation hypothesis often assumes one can reproduce known physics with an unspecified algorithm while ignoring the difficulty of matching symmetries, general relativity, quantum fields, and small-scale processes. This critique is valuable because it demands mechanism. How would the simulation reproduce the foundations of physics to high precision? What algorithm? What substrate? What compression? What happens when observers probe shorter distances? Without answers, the hypothesis remains underdeveloped. A scientific claim should not be allowed to hide behind future technology indefinitely. Future technology may change what is possible. It does not change what has been demonstrated. This is why I will not say that advanced civilizations could never simulate conscious beings. I will say that no known human technology could, that the physical requirements are severe, that the nature of consciousness is unresolved, and that broad claims require assumptions. I will not say cosmic rays have shown a lattice. I will say they provide a possible way to constrain a lattice-like simulation model. I will not say Lorentz invariance rules out simulation. I will say it strongly constrains simple, preferred frame or grid-like physics. I will not say information physics proves the universe is code. I will say information physics makes computation physical and therefore constrains any simulator governed by similar laws. I will not say quantum mechanics means reality renders on observation. I will say standard quantum theory already accounts for interference, measurement statistics, and decoherence without requiring conscious rendering, though interpretations remain debated. I will not say the question is meaningless. I will say its scientific meaning depends on the model. The difference between these statements is the difference between narration and evidence. The ship's exterior cameras show a faint band of dust ahead, a remnant of some old collision between bodies too small to name. The navigation system adjusts without drama, tiny particles, high velocities, real consequences. The universe does not need to be theatrical to be dangerous or beautiful. It is enough that it is consistent. Consistency is the quiet hero of the file. The simulation hypothesis becomes hard to detect if the simulated world is consistent. Yet consistency is also what makes science possible inside it. A world full of arbitrary glitches would reveal its artificiality, perhaps, but it would not support deep science. A world with stable laws supports science and hides its substrate. The very success of physics could be read either way, as evidence of a lawful base reality or as evidence of an excellent simulation. Without a distinctive prediction, the readings are empirically tied. That tie is frustrating. It is also clarifying. The question, what is real, may not always have the same answer as what can be measured. Science lives with that gap. It does not deny it. It builds bridges only where evidence can support them. In the last pages of the file, the handwriting changes. It may have been a student's note copied from a lecture. It reads, "If a claim explains everything equally, ask what it forbids." I underline it. What does the simulation hypothesis forbid? In its broad form, nothing. Any observation can be part of the simulation. What does a cubic lattice forbid? Perfect continuous rotational symmetry at all energies, depending on the model. What does a same physics simulator forbid? Unlimited detail without energy, memory, and entropy costs. What does a Bayesian simulation argument forbid? Careless certainty, once model uncertainty is included. What does a rendering model forbid? It may forbid certain relationships between physical records and observed outcomes if stated sharply enough. The work is to move from the first kind of claim to the latter ones, from everything to something, from awe to risk. The archive's voice recognition system asks for a final classification. I choose philosophical hypothesis with testable physical submodels. That is the most accurate label I can give. Aboard the ship, labels matter. A mislabeled specimen can poison a century of reconstruction. A mislabeled signal can become a false discovery. A mislabeled philosophical argument can masquerade as physics. The simulation file teaches that category errors are not small mistakes. They change what one thinks has been proven. Bostrom's trilemma is a philosophical probability argument. Kipping's paper is a Bayesian critique and refinement. Lloyd's work is physics of computation. Bekenstein's bounds are entropy and information constraints. Georgescu, Ashab, and Norrie's review concerns quantum simulation as a real field. Mattingly and Liberati review Lorentz invariance tests. Bean, Davoudi, and Savage propose observable consequences for a specific lattice simulation scenario. Vaza estimates astrophysical and information energy constraints. Vopson proposes a speculative information dynamics route. Campbell and collaborators propose controversial quantum-style tests for a rendering model. Each has a place. None should be made to do another's work. The script of the universe, if there is one, has not been recovered. Only the case notes have. The final scientific question becomes almost modest. Can we find evidence that the laws we observe are approximations produced by a deeper computational structure? That is close enough to physics to proceed. To answer it, one searches for approximation errors. Lattice artifacts, symmetry violations, resolution limits, unphysical correlations, resource constraints, deviations from known laws at extreme scales. One also searches for conventional explanations and gives them priority when they work. This is not bias against simulation, it is the ordinary economy of science. Do not add a parent universe when a local model explains the data, but do not forbid the question either. Human science advanced by asking whether appearances were incomplete. The Earth appeared still. It moved. Space and time appeared separate. They were linked. Matter appeared solid. It was quantum. The vacuum appeared empty. It seethed with fields. A question that sounds strange is not automatically wrong. It simply owes evidence. I place the folder back on the desk and open a blank page for the closing reconstruction. The lamp reflects in the observation glass, a small, warm rectangle overlaid on distant stars. For a moment, the reflection looks like a window inside the window, a room inside the sky, an image layered over a reality I cannot touch directly. It would be easy to make too much of that. The archive's style guide would object. A reflection is not a simulation. It is only a reminder that appearances can have layers. The work is to determine which layers leave measurable traces. The old humans did not know whether their universe was fundamental. Neither do I. What they did know, and what survives, is how to ask better versions of the question. They knew that probability arguments depend on assumptions. They knew that information has physical cost. They knew that quantum systems are hard to simulate. They knew that space-time symmetries can be tested. They knew that cosmic particles can probe energies beyond their machines. They knew that a hypothesis protected from every possible result stops being a scientific instrument. That is not a small inheritance. The simulation file is not a confession from the universe. It is a record of discipline applied to wonder. If reality is simulated, then somewhere beneath our equations there may be another structure, another physics, another system bearing the cost of our sky. But if that structure leaves no trace, then our task remains what it has always been: to study the world available to evidence, to measure carefully, to compare models, to admit uncertainty without surrendering to it. The universe may have a deeper layer, it may not. The stars outside the observation dome do not answer. They send light, and light, for now, is enough to begin. There is one more section of the recovered file that deserves patience. It concerns what a meaningful future detection might look like. Humans often wanted discoveries to arrive as clear revelations. A signal, a message, a line of code hidden in the cosmic microwave background, a pattern of prime numbers in the constants of nature, a visible edge to reality. The archive contains many such fantasies. Science rarely grants discoveries in that form. A real anomaly would likely begin as an error bar that refused to shrink. A pattern in cosmic ray arrival directions that remained after exposure corrections. A time of flight delay in high energy photons that matched an energy dependent law and appeared across many sources. A threshold reaction occurring where ordinary Lorentz invariant physics forbade it. A laboratory measurement disagreeing with theory after every conventional correction had been exhausted. A statistical residue in the sky that tracked a symmetry group too specific to ignore. Even then, the first conclusion would not be simulation. The first conclusion would be new physics. This is worth emphasizing because it protects the episode from false drama. Suppose future observatories found evidence of Lorentz invariance violation. That would be revolutionary. It might suggest quantum gravity effects, emergent spacetime, preferred fields, modified dispersion relations, or other beyond standard model physics. A simulation interpretation would be one candidate only if it predicted the same signature cleanly and economically. The evidence would have to pass through layers of ordinary scientific caution before reaching anything like simulated universe. The same would be true for lattice-like cosmic ray anisotropy. A cubic pattern at the highest energies would be astonishing, but astrophysical source distributions, magnetic field structures, detector systematics, exposure effects, and unknown particle physics would need to be examined. The simulation model would have to outperform alternatives. Only then would it deserve serious standing. A simulated universe would not be discovered by vibes. It would be inferred by stubborn residuals. The file includes a damaged note on signatures. I restore what I can. A signature is not simply an unusual fact. It is an unusual fact tied to a mechanism. Smoke is a signature of fire because combustion produces it. Spectral lines are signatures of atoms because electron transitions produce them. Gravitational waves are signatures of accelerating masses because general relativity predicts ripples in spacetime. A simulation signature must be tied to the method of simulation. Without the method, the signature is only an interpretation. This is why the cubic lattice proposal is so valuable as an example. It ties a possible signature to a possible mechanism. A finite hypercubic grid breaks certain symmetries. Those broken symmetries may affect high-energy particles. Therefore, look at the most energetic cosmic rays. That chain can be questioned, but it exists. Many simulation claims have no such chain. In the evidence bay, I project several hypothetical claims and ask the archive to classify them. The universe is mathematical, not a simulation signature. The constants appear fine-tuned. Not by itself, many interpretations exist, including selection effects, multiverse models, unknown necessity, or incomplete theory. Quantum measurement is strange. Not a simulation signature unless a simulation model predicts deviations from quantum theory. The Planck length exists, not a pixel signature. Cosmic rays show cubic anisotropy at extreme energies. Potential signature under a specific lattice model. Information erasure has a thermodynamic cost. Constraint on simulators under similar physics. No experiment could ever reveal the truth. Not scientific. The classifications are cold, but useful. Fine-tuning deserves a brief entry because it often appears in simulation discussions. The constants of physics allow long-lived stars, chemistry, complex structures, and life. Some have argued that such apparent tuning suggests design or selection. Others point to anthropic reasoning. Observers can only arise in regions or universes compatible with observers. Others hope for deeper physical laws that determine the constants. Simulation is one possible design-like interpretation, but it is not uniquely supported by fine-tuning. Without a model predicting the constants from simulation requirements, it remains suggestive at most. The same caution applies to mathematical elegance. The universe's laws can be written mathematically because mathematics is the language humans developed to describe patterns. That does not mean the universe is made of human-style code. Mathematical describability is a feature of successful science. It is not evidence of an external programmer on its own. The old records show that humans often confused map and territory. A simulation hypothesis must not repeat the error by confusing equation and software. Another possible route concerns randomness. If the universe was simulated by an algorithm using pseudo-random number generators, perhaps deep statistical patterns would reveal non-randomness. This idea appears often in informal fragments. In principle, one could search for unexpected correlations in quantum outcomes, cosmic backgrounds, or particle events. In practice, the idea is weak unless the simulation model specifies the generator, the expected correlations, and why ordinary physics would not produce them. Quantum randomness has been tested in many ways, including Bell tests and device-independent randomness protocols. Those tests constrain local, hidden variable models and support quantum predictions, but they do not automatically test simulation. An external simulator could produce genuine randomness from its own physics, or pseudo-randomness too good to detect, or a deterministic process that reproduces quantum statistics. Again, the broad hypothesis retreats. Only a specific one can be tested. The file's repeated lesson is almost tedious. That is good. Some truths should be allowed to become sturdy through repetition, though not through rhetoric. Specificity is the price of testability. I step into the specimen archive and remove a small sealed wafer from storage. It is a piece of old detector material recovered from a lunar debris field. Its surface is etched with microscopic tracks left by charged particles. Each track is a history of interaction. A particle crossed, deposited energy, disrupted bonds. The wafer did not know what crossed it. It recorded what physics allowed. The best simulation test would be like that. Not a philosophical mood, but a track. The detector wafer also shows why absence matters. If a theory predicts many tracks and none appear, the theory suffers. If a theory predicts that tracks may or may not appear depending on unknown choices, absence teaches less. The broad simulation hypothesis often makes no mandatory tracks. That is why it survives. It is also why it remains scientifically thin. Some viewers may feel that this caution drains the subject of its wonder. I think it does the opposite. It removes the cheap wonder and leaves the durable kind. The durable wonder is that humans could ask this at all. A species of primates on a rocky planet built instruments sensitive to quantum fields, space-time curvature, high-energy particles, ancient radiation, and gravitational waves. They built simulations of the forces inside atomic nuclei, then used those simulations as analogies for the possibility that their own world might be simulated. They turned metaphysical doubt into proposed measurements of cosmic ray anisotropy. That is an astonishing arc, even if the answer is no. Especially if the answer is no. If the universe is not a simulation, then all this structure, law, difficulty, and beauty is not an artifact of apparent calculation. It is simply what reality is. That is not a lesser conclusion. The case file should not treat base reality as boring. It is not. A non-simulated universe contains quantum fields, black holes, entropy bounds, emergent complexity, consciousness, galaxies, chemistry, life, memory, and beings who wonder whether they are simulated. That is enough. If the universe is simulated, then the question becomes different, but not necessarily more profound. We would ask what kind of parent system can produce such a world, what moral status simulated beings have, whether the parent reality is itself fundamental, and whether an infinite regress is possible or meaningful. The first simulation does not remove the old question. It pushes it upward. What is the simulator's universe made of? Is it simulated? What grounds that reality? At some point, the chain either ends, loops, dissolves, or becomes a question beyond physics. The simulation hypothesis can relocate the mystery. It does not automatically solve it. This is another reason probability arguments about nested simulations require care. If simulated realities can produce simulated realities, the numbers grow quickly. But resources, degradation, and purpose matter. A chain of worlds is not only a tree of counts, it is a chain of physical burdens, unless the parent layers have laws that make the burden irrelevant. If they do, our physics cannot evaluate them. The archive table displays a nesting diagram, boxes inside boxes inside boxes. After the 4th level, the lines blur. After the 7th, the visualization fails. I shut it down. Infinite regress is not evidence. The vessel's clock advances. Time inside this ship is measured by oscillations, signals, and relativistic corrections. It is a practical thing. In a simulation, time might be implemented differently. A parent computer could pause a universe, run it faster, rewind it, branch it, or compute it timelessly as a complete block. From inside, inhabitants might still experience time according to internal laws. This connects to another philosophical issue, whether simulation requires step-by-step updating. Human intuitions about computation were sequential because many of their machines were, but some physical systems solve by evolving continuously. Some mathematical descriptions treat the whole space-time history as a 4-dimensional structure. A simulated universe might not be rendered frame by frame. It might be generated as an entire solution, sampled as needed, or represented in ways that do not correspond to internal time. Therefore, arguments based on processing each moment must specify their model. A digital time-step simulation has one set of constraints. A path integral-like or block universe representation has another. An analog quantum simulator has another. Some constraints remain because information and physical representation still matter under known laws, but the details change. This is why language must be kept plain. The universe is running may be a metaphor. A metaphor should not become an assumption unnoticed. There is a recovered note from a philosopher of science. Underdetermination does not mean all theories are equal. Two models may fit current data, but differ in simplicity, coherence, fruitfulness, and connection to other knowledge. The simulation hypothesis, when broad, can fit any data, but only by adding hidden machinery. A base reality model with known laws may be simpler until evidence requires more. Simplicity is not proof, it is a guide. Scientists often prefer the model that explains the evidence with fewer unsupported entities. This is sometimes called Occam's razor, though the archive contains many versions and misuses of it. The razor does not say the simplest story is always true. It says not to multiply assumptions without need. A simulator is a large assumption. It may be justified someday. It is not justified merely by possibility. I think of the archive itself. If I find a page with scorch marks, I do not first assume it was damaged by a ritual fire lit by unknown beings for symbolic reasons. I look for heat, radiation, chemical exposure, storage failure, impact. Ordinary causes first. If ordinary causes fail, stranger ones may enter. That is not closed-mindedness. It is how finite reason avoids drowning. The simulation file has too often been handled backward. It begins with the strangest possible cause, then looks for facts to absorb. The scientific reconstruction begins with facts and asks what causes they require. What facts require simulation today? The honest answer is none. What facts could someday support a simulation-like model? Symmetry-breaking artifacts, finite resolution effects, computational anomalies tied to a clear mechanism, or some other specific prediction not yet imagined. That is enough to keep the file open. The final shipboard transition takes me to the observation dome itself. The dome is darkened to reduce internal reflections. The stars are sharp. Somewhere beyond the visible field, cosmic rays pass through the hull, most unnoticed. Neutrinos pass through almost everything. Photons arrive from sources that no longer exist. The ship is an instrument surrounded by events. This is the right place to return to the human position inside the universe. They were always inside the system they studied. They could not step outside space-time to inspect it from above. They inferred. They built local instruments. They compared observations made from one location with laws that seemed to hold everywhere. Their science was an inside job from the beginning. The simulation hypothesis makes that condition explicit. If we are inside a generated world, we cannot inspect the generator directly. But even in base reality, we cannot inspect reality from outside itself. Science has always been the art of internal inference. That thought reduces the strangeness of the question. We have never had absolute access. We have had evidence. The old astronomers did not need to leave the solar system to infer the structure of planetary motion. They did not need to stand outside the galaxy to map it. They did not need to enter a black hole to calculate its thermodynamics. They used traces: light, motion, spectra, timing, statistics, theory. If the simulation hypothesis ever becomes scientific in a strong sense, it will be through traces too. The trace might never come. That possibility is not failure. Many possible truths may leave no trace accessible to us. The mature response is not to pretend otherwise. It is to mark the boundary and continue studying what does leave traces. In the observation dome, the ship's systems overlay a simple line across the glass. Evidence recovered. Verdict pending. I leave it there. The closing of this case file should not sound like a door slamming. It should sound like a folder returned to the archive with better labels. The simulation hypothesis began as an ancient human unease reborn in computational language. It became famous through a probability argument about future civilizations and simulated minds. It gained scientific edges when physicists asked about computation, information, quantum simulation, spacetime lattices, cosmic rays, and Lorentz symmetry. It became more constrained when energy costs and entropy bounds were taken seriously. It remained unresolved because the broadest versions make no distinctive predictions. So the answer to "are we living in a simulation?" is not yes. It is not no. The scientific answer is, tell me what kind of simulation, and I will tell you what can be tested. If it is a finite lattice, look to the highest energy particles and the symmetries of space. If it is a physical computer under laws like ours, count energy, memory, entropy, speed, and heat. If it is an ancestor simulation argument, examine survival, motive, consciousness, and priors. If it is a quantum rendering claim, demand predictions beyond standard quantum mechanics. If it is an undetectable, perfect construction, admit that science has no instrument for it. That may be the most careful reconstruction humanity left us. I close the folder and the lamp dims automatically. Outside the observation dome, the stars remain. Whether they are fundamental or computed, their light follows the laws available to measurement. It redshifts across expansion. It bends near mass. It scatters from dust. It arrives in quanta. It carries spectra, temperature, polarization, and time. A simulated star, if it obeys those laws perfectly, can guide a ship. A real star, if that is the better word, does the same. From inside the universe, knowledge begins with the light that reaches us. The case file returns, at last, to its first warning. Distinguish question from model. The question can remain large. The model must be precise. The wonder can remain intact. The claim must earn its evidence. Long after the old networks of Earth went dark, that is what survives most clearly. Not certainty about the deepest layer of reality. Not proof that the stars are base reality, or proof that they are computed. What survives is the method. Ask what follows. Measure what can differ. Keep track of uncertainty, and do not mistake the ability to imagine a hidden world for evidence that one exists. The universe may have a substrate beneath the one we know. It may not. But the scientific path does not begin by escaping the world. It begins by listening carefully to the world we can test. The folder is sealed now. Testability status. Limited, model dependent, active. And beyond the glass, the dark remains full of measurements waiting to be made.